This video is your last video, and it is for section 12.12. So, first let's talk about what it means to transform to achieve linearity. So in Chapter 3, we learned how to analyze relationships between two quantitative variables that showed linear pattern. Now we will look at new techniques for finding an appropriate model when our data shows a curved relationship. And we will do this by transforming the data to straighten out any nonlinear pattern that we have. So basically, we'll start with a scatter plot that has some sort of curvature, and we'll figure out a way that we can flatten out that curvature and make it into a straight line. So one of the ways that we could possibly do that is by transforming with roots and powers. So we'll start talking about the power model. So the power model says that y is equal to a times x to the p. So here are some examples of what the power model might look like. So the distance of an object dropped from a given height falls is related to time since released by the model. Distance equals a times time squared. So basically, what that means is we can take a situation and we can write an equation for it that is in this particular model. So the time it takes a pendulum to complete one back and forth swing, its period, is related to its length by the model. Period equals a times the square root of length. But we can rewrite a times the square root of length by saying a times length to the 1/2 power because of rational exponents. So remember that this is an imaginary little 2 out there, so your index on any square root is always a 2, and the number of times that you have length underneath that root is 1, and that's how we get to the 1/2 power. Alright, the intensity of a light bulb is related to distance from the bulb by the model. Intensity equals A divided by distance squared. We can rewrite this though so it looks like a power by saying I have a positive exponent on the bottom, but if I moved that exponent and all of its belongings to the top, it would make it a negative exponent. So even though it's a negative exponent, it's still okay for this one because we were trying to make it look like this particular model. So although a power model of the form y equals a times x to the p describes the relationship between x and y in each of these settings, there is a linear relationship between x to the p and y. If we transform the values of the explanatory variable x by raising them to the p power, and graph the points x to the p, y, the scatter plot should have a linear form. So basically, by rewriting these so that we were able to have a power model, we have created a linear form when we go to graph points based on these situations. So here's an example. So imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat, but what you need is a way to convert the length of the fish to its weight. You contact the nearby Marine Research Laboratory, and they provide reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish for several sizes. So they give you a table basically that shows you different lengths and the weights that kind of correspond with those particular lengths. So in figure 12.12, which is this one, we see a scatter plot of the data that was given to us here. And it's important that you notice that it starts to kind of have this curved shape. So because length is one-dimensional and weight, like volume, is three-dimensional, A power model of the form weight equals A times length cubed, cubed because it's volume, it can be like volume and three-dimensional, should describe the relationship. What happens if we cube the lengths in the data table and then graph the weight versus the length? Figure 12.13 gives us the answer. So this transformation of the explanatory variable helps us produce a graph that is quite linear. So by taking these points and by plugging them into this particular model here, which is a power model, where we have weight equal to A times the length cubed, we can take these points and straighten them out and create a straight line. So the power model is not the only way that we can transform data to create a linear pattern out of a nonlinear pattern. We could also use logs to do that as well. So if I see log equals like y, or y equals a plus b times log x, this looks kind of similar to y hat equals a plus bx. So if I were to graph this, it would give me something that was similar to this, which would be like a straight line. But if I'm looking at an exponential like y equals ab to the x, this one doesn't look at all like this. So what I have to do is I have to get this x out of the air. And to do that, the only way I can get an exponent out of the air is to log both sides. So I'm going to log both sides so that it looks like this. And because these two things are together, I can split them up. This also takes this x and puts it out front. So now when I see this, I see that log A is one thing, like a constant, and I see log B like the slope. So we have it a little bit backwards from what you usually see it. So if you wanted to rewrite it so that the x was at the end, it would be even more similar to the y hat equals a plus bx. So now I have created something that whenever I graph it is going to give me something that looks like this. So check your understanding. The following table gives the resident population of the United States from 1790 to 1880 in millions of people. The graph at the left here is a scatter plot of these data since 1700 as the explanatory variable. A plot of the natural logarithms of the population values against years since 1700 is shown to the right below. So what they did here was, this was the original, and you can see that it's got a curved pattern, and this was the transformation. For the transformation, they used an ln. So ln, you may remember from a long time ago, stands for a natural log, and a natural log is going to cancel out e. This part's going to be important later on. So number 1 says, explain why it would be reasonable to use an exponential model to model the relationship between the U.S. population in years 1790 to 1880 and the number of years since 1700. So when I look at this, I see that the second graph was a natural log, like we talked about. So we would say because the second graph was a natural log, ln, and showed, ooh, that was not good, and showed a linear pattern. This suggests the original data must be described as an exponential. Which is what we were talking about up here. It goes on and it says, here is some mini-tab output from linear regression analysis on the transformed data. So then you've got this. That will be helpful because question 2 says, give the equation of the least squares regression line and define any variables that you use. So for number 2, we'll go back to our mini-tab output, and we'll use this information here to write our least squares regression line. Now, remember that our least squares regression line is for this graph, which was the straight line graph, which was also the LN graph. So what we're going to do is instead of doing y hat, it's going to be ln y hat. So ln y hat is equal to the numbers from here, so negative 1.193 plus 0.0287 x, where y is the population and x is years since 1700. 3 says use the linear model to predict U.S. population in 1890. Alright, so if I'm doing years since 1890, remember that x is years since 1700. So I would do 1890 minus 1700 and get 190. So this is the value that I'm going to plug in for x. So then I'm going to use my predicted ln y hat equals negative 1.193 plus 0.0287 times 190. Whenever you do that, you get 4.26. $4.26 though is the value that we're going to plug into the original. So to do the original, that's going to tell me the predicted population. So because I knew that it was an ln, we said that that had to do with e. So what that's going to look like is the original y hat would be e to the x. We know that x is going to be 4.26, so e to the 4.26. E is a button on your calculator, and so your calculator will do all the work for you. So you're going to do second divide, and that gets you e to the 4.26, and that's going to give you 70.81. So that means that the population is 70.81 million people. And I know it's going to be million people because it said that my information was in millions of people. 4 says, based on the residual plot, which is here, do you expect your predictions to be too high or too low? Justify your answer. So on your residual plot, your x values are your years since 1700. And we calculated that for number 3, we were going to use 190. So if I'm thinking about 190 would be way over here somewhere. And so if we were just kind of predicting what was going to happen, that would take our value to be something that was negative. So the residual plot suggests that the residual for this point would be negative. And I know it's going to be negative because all these values underneath here, underneath the residual equals 0 line, are going to be negative. And so we've seen at 180 we were in the negatives, so we would predict that 190 would also be in the negatives. So because we're saying that our residual would be in the negatives, that would mean that the prediction is too high. The reason that the prediction is too high is because remember that your residual calculates your observed minus your expected. So the only way that we could get a residual that was negative would be if our residual was smaller than our expected, because our expected here is going to be negative since we're subtracting it. So the only way we can get a residual that's going to be negative is if our expected value is much higher than our observed value.